So let's start. Good day and welcome to this International Energy Agency webinar on energy and artificial intelligence hosted by the Fondazione Eni Enrico Mattei. My name is Filippo Del Grosso. I'm a senior researcher here at the Fondazione Eni Enrico Mattei, and I will be the moderator for today. Just allow me a few words on the hosting institution of this event. The Fondazione Eni Enrico Mattei is a research center and think tank headquartered in Milan, covering the aspects of energy and sustainability across 7 different research programs. Today, we are pleased to partner with the International Energy Agency in delivering this webinar for you. When we talk about the energy transition, at least here in Europe, we somehow tend to focus on the supply side of the energy equation. For instance, how many renewable we need to achieve our decarbonization targets by 2030. On the other hand, the deployment of artificial intelligence is one of the biggest challenges in this brave new world ahead of us, and forces us to reconsider our perspectives in terms of energy demand. These aspects are thoroughly investigated in the latest report published in April by the International Energy Agency. Today, we have the pleasure of having 2 great speakers to help us exploring this topic. Thomas Spencer is our keynote speaker for today. He's a senior analyst at the International Energy Agency and lead co-author of the report. He will present us the key insights of the analysis. Thank you very much for your time and availability, Thomas. Welcome to Fondazione Enrico Mattei.
Thank you so much. Happy to be here.
After Thomas, there will be a discussion session presented by my colleague Sara Zanini. Sara is a PhD candidate at the Venice School of Management at the Ca' Foscari University of Venice and a researcher here at the Fondazione Enrico Mattei. Recently, Sara contributed to the methodological report for a main European data center company, covering the topic of 24/7 carbon-free energy in the context of sector capping. Again, thank you for being here today, Sara.
Thank you, Filippo, and good morning, everyone.
Excellent. So, without any further delays, I would leave the floor to Thomas for his presentation, Energy and Artificial Intelligence. The floor is yours, Thomas. Over to you.
Thank you so much. I will just share my screen. Just confirming that this is coming up okay.
Yes, all good.
Okay, great. Well, thank you very much, Filippo, for the very kind introduction, and to FEEM for the invitation to the International Energy Agency to be here today. FEEM and the IEA have been collaborating for many, many years, so we're extremely happy to be a part of the discussion today. So I'm going to present the key findings of our special report on energy and artificial intelligence, which we published in April this year. Maybe before I do so, just to say that the IEA has been working on the topic of energy and digitalization for some time. In 2017, we published a report on energy and digitalization. We have been tracking the electricity consumption of data centers for a number of years. And of course, as part of our data collection and our modeling, we also model the electricity consumption of the IT sector more broadly. But it is fair to say that in the last, let's say, 24 months, last 3 years, there has been a step change in the rise of importance of artificial intelligence for the energy sector, but also for our economies more broadly. One of the key turning points was the release of ChatGPT in 2022, which really for the first time brought to the public's awareness the possibility of artificial intelligence models providing useful services for our day-to-day lives. But of course, artificial intelligence is not new. The field has been around academically since the 1950s. But in the last few years, we have seen a step change in the capability of artificial intelligence models based on cheaper and more abundant computing, more data availability with the rise of the internet and digitalization more broadly, and technical breakthroughs in the design of AI models. So on the screen, you can see a chart which shows the amount of compute that is used to train the leading AI models. This has grown by 1 trillion times since 2006 and is doubling more than annually, so doubling roughly every 8 or 9 months. With the rise of more useful AI models, we can see that economic interest in the sector is growing as well. One indicator of this is what is happening in the stock market. So if you look at the increase in the market capitalization of the S&P 500, AI-related companies provided 60% of the market cap increase since November 2022. In dollar terms, this is equivalent to an increase in market capitalization of 12 trillion US dollars. This is a significant bet on the future economic productivity that AI can bring. So this is the broader context for our interest in the question of the impacts of artificial intelligence on the energy sector. If we want to understand the impacts of artificial intelligence on the energy sector, we need to look at data centers. The reason for this is that today, the leading AI models are too large to be run on our phones or on our laptops. So instead, they are trained and run on specialized hardware in data centers. Now, data centers are quite unusual kinds of energy infrastructure for 3 reasons. The first reason is that they tend to cluster close to urban areas. So what you can see on the screen is real data. This is based on a GIS analysis that we did of the roughly 11,000 data centers that are currently in operation around the world. And what you can see is that in comparison to other kinds of energy infrastructure, they are located much closer to urban areas. The other aspect of data centers that is important is that they tend to cluster together. So where you get one data center, you will get several. And then finally, the third characteristic is that data centers are getting larger. So today, a hyperscale data center might have a power draw of about 100 megawatts. In terms of annual electricity consumption, this is equivalent to the electricity consumption of about 100,000 households. The largest under construction has a power draw of 2 gigawatts, and the largest proposed has a power draw of 5 gigawatts. To put this in perspective, a large aluminium smelter might have a power draw of about 750 megawatts. So we are talking about extremely large pieces of energy infrastructure, which tend to cluster together, tend to locate close to urban areas, and therefore in areas where electricity grids may already be congested. The fourth characteristic of data centers is that they can be constructed much more quickly than other kinds of energy infrastructure of a comparable size. So to construct a new manufacturing facility, we might be talking about a process that can take years. To construct a transmission line, a process that can take 4 to 8 years or even more in advanced economies. But a data center can be developed and built in as little as 18 months. And so this creates a new kind of challenge for our energy systems. So this raises the question of how much electricity do data centers consume today? This is not an easy question to answer because there is no good data on this topic. Governments don't collect comprehensive statistics on the electricity consumption of data centers. Companies from the IT industry generally do report their electricity consumption, but they don't break down their electricity consumption of data centers. So a company like Amazon will provide you its total electricity consumption, but that includes its office buildings, its warehouses, but also the data centers. And so this makes it challenging for us to estimate total electricity consumption of data centers. So what we did for the report was build a model of electricity consumption from data centers using multiple sources, including third-party data providers, including sources from industry, from governments. What we find is that today data centers consume about 415 terawatt hours of electricity. That's about 1.5% of total electricity consumption globally, which is about 27,700 terawatt hours. So just to put that in perspective. But data center electricity consumption has been growing rapidly. It's been growing at about 12% per year over the last 5 years at the global level, which is about 4 times faster than the underlying rate of total electricity demand growth. Looking forward in our modeling, we project that data center electricity consumption will roughly double by 2030 in our base case, reaching about 945 terawatt hours of electricity consumption. This is more than the total electricity consumption of the country of Japan, so it's a significant amount. By 2035, we project the data center electricity consumption would triple relative to today, although there is a lot of uncertainty about these longer term figures. Looking at the major driver of this, we can see that AI is not the only driver of the increasing electricity consumption growth of data centers, but it is the predominant driver. This being said, there is no easy way to estimate what share of data center electricity consumption comes from AI. So what we have done is in our model distinguish between what we call conventional servers. So these are servers with a computing architecture based around central processing units, so classic computing chips, and then what we call AI optimized servers. So these are servers based around a computing architecture with accelerated chips such as graphics processing units or other specialized chips which are tailored to AI-related operations. And so what you can see is that the electricity consumption of these AI-optimized servers is quite small today, but it provides by far the largest share of the growth going forward into the future. At the global level in 2030, electricity consumption from data centers would still be equivalent to about 3% of total electricity demand. And if we look at the share of data centers in the growth of electricity consumption, we see that it accounts for about 10% of the growth in global electricity consumption to 2030. But the picture is quite different in different regions. In emerging market and developing economies, electricity demand is growing already rapidly for multiple reasons, including industrialization, rising incomes, increasing purchase of electricity consuming equipment like air conditioning. And these economies tend to be less digitalized than advanced economies. And so for these reasons, data centers account for a lower share of electricity consumption growth in emerging market and developing economies. On the other hand, the picture is very different in the United States or in advanced economies more broadly. Advanced economies have seen more or less stagnant electricity demand for the last 2 decades. That is starting to turn around as we electrify energy consumption for climate policy reasons. But data centers are another important source of electricity demand growth in advanced economies. In the United States, data centers account for as much as 45% of the increase in electricity consumption between now and 2030. And by 2030, data centers in the United States would consume more electricity than all of the energy-intensive industries combined. So that's iron and steel, cement, chemicals, aluminium smelting, and so on. So quite an extraordinary evolution in the structure of the United States energy consumption. Looking at the supply mix to meet this increase in data center electricity consumption, we see a strong role for renewables based on their economic competitiveness in many regions, based on the fact that renewables projects can be developed relatively quickly, but also based on the fact that many IT companies have strong sustainability targets and are quite active in procuring power purchase agreements for renewable electricity. In the longer term, there's also a role for nuclear power. We see today some IT companies starting to procure nuclear power from existing nuclear reactors in the United States, but also IT companies making forward commitments to novel energy generation technologies like small modular reactors, but also advanced geothermal technologies. So just to give you an example, we track about 25 gigawatts of small modular reactor projects that have received forward commitments from the IT sector. There's also a role for natural gas in regions where natural gas is readily available and cost effective, so notably in the United States. And we see data centers also being powered by coal in places like China or India. Now, the issue of energy security is core to the mandate of the IEA. It's something that we monitor very, very closely. And the rising importance of data centers and artificial intelligence within the energy sector is creating new issues for energy security. One of these is supply chains, and this has numerous facets. So, for example, to connect a data center to an electricity network, you need a transformer. The wait times for transformers have increased dramatically over the last 3 years. They've roughly doubled, while prices have also increased by about 75%. So that's one example of where supply chains and supply chain security play into the rise of artificial intelligence. Another aspect is the use of critical raw materials in data centers. So if we take the example of gallium, for example, which is being used increasingly in high performance power electronics needed to connect the sophisticated electrical equipment within data centers, but also in the latest generation of computer chips that are being put into data centers. We estimate that data centers could account for new gallium demand equivalent to about 10% of today's gallium production. And when we look at the geographical concentration, we can see that a single country, namely China, accounts for 99% of total gallium refining today. Another aspect of energy security is cybersecurity, and AI is creating both new risks but also new opportunities to strengthen cybersecurity defenses. So at the IEA, we track cybersecurity incidents for energy utilities. These have tripled in the last 4 years, and we see very clearly that AI is being used to make cyber attacks more potent, but also to defend against cyber attacks. And so how we think about the use of AI tools to defend against cyber attacks, how we think about the necessary skills that companies need to hire into the energy sector to ensure that we have the necessary digital skills to ensure cybersecurity will be important issues going forward. The final issue related to energy security is a bit of the reverse of the coin, the other side of the coin, and it relates to the risks that insufficient build out of energy infrastructure could pose to the development of data center projects. So what we did in the report was look at the data center projects that are currently under development, and we found that roughly 1/5 of these could be at risk of delay due to grid congestion, due to slow connection times, and due to slow build out of generation assets. Of course, there are solutions to these challenges. We need to look at cutting permitting times for energy infrastructure. We need to look at making our electricity systems smarter and more efficient. And we need to look at how we can optimize the location and operations of data centers. Finally, there is the issue of what does all of this mean for climate change and emissions? So today, the electricity consumption of data centers accounts for emissions equivalent to about 180 million tons. This is less than 1% of total global emissions. In our worst case scenario, with the highest electricity consumption from data centers, this rises to about 500 million tons by 2035, equivalent to about 1.5% of global emissions. However, there is another side of the coin, which is the potential for AI solutions to improve efficiency and facilitate the rollout of low emissions technologies in the energy sector. This is something that we looked at in a lot of detail in our report. Opportunities include, for example, using AI tools to better operate the power system, reducing curtailment of renewables and enhancing the use of existing transmission infrastructure, using AI-related tools to optimize energy consumption in heavy industry, or using AI-related tools to optimize route selection for example, freight and logistics. When we look at only existing use cases that have proven benefits, we see that emissions reductions from the application of AI-related tools could be quite substantial. But there's not a given that these emission reductions are achieved. We need to make sure that we have the right skills, the right incentives, and the right policy frameworks. And finally, of course, there is the risk that AI-related tools could lead to rebound effects. So the classic example of this would be a shift from public to private transport if autonomous vehicles become more widely available. These rebound effects are very difficult to quantify and very uncertain, but something that we definitely need to keep an eye on. But the key message from our report was that if we look across all of the use cases of AI, from innovation to optimization of our energy system, if we look at the direct and possible indirect footprint of AI, we see that it's not really a game changer for climate change. It can be a useful tool in our fight against climate change, but it doesn't remove the need for us to do what we have been needing to do for a long time now, which is focus on energy efficiency, focus on rolling out already available low emissions technologies. So with that, I will stop the presentation and I look forward to the discussion and the questions.
Thank you very much, Thomas. As of now, we don't have any questions, but my bad, because I had actually to tell people that they can write on the chat box in our chat. I thought it was rather implicit, but please, if you have any questions, write in the chat box and we will forward them to the two speakers and we will try to answer as many as we can. There is only one administrative question for you. They are asking whether, Thomas, it will be possible to share your presentation at the end of the event.
Yes, that's no problem. And the report is freely available online as well.
Okay, thank you very much. So it will be made available on our communication channel. Okay, so please, you can answer your question in the chat box in the meanwhile. But before that, I'm leaving the floor to Sarah for the discussion question. Sarah, over to you.
Thank you, Filippo, for leaving the floor. I'm going to share my screen. You should be able to see my presentation. I just wait for you to confirm me.
Yes, all good.
Okay. So first of all, thank you, Thomas, for explaining us the content of the International Energy Agency report. And I obviously start a discussion from the report itself. I wanted to put a spotlight on a specific chapter as in the research group that I'm involved in, Enrico Mattei Foundation. We study the electricity market and the electricity system. So one of the chapters which we're most interested in was the chapter 2.5, electricity supply for data center demand. And this graph is indeed from the chapter itself. Where you are showing the result of a study, a comparison between, first of all, annual matching and hourly matching of different solutions in terms of portfolio of energy mix to supply data center demand. But what I wanted to underline as a primary concern here is the difference between pursuing an annual matching calculation or an hourly matching calculation. Annual matching means that we try to understand whether there are as much as renewable energy sources to supply data center on an annual basis, while with the hourly matching, we try to go deep into the detail of the hours themselves. The result of this analysis, and maybe we'll leave Thomas to discuss it better at the end because he's a co-lead author of the report, is that 80% hourly matching, low emission portfolios are comparable in cost with annual volume matching project in the United States. So you found out that actually there are cost competitive solutions, even pursuing an hourly matching, which allow to reduce emission. You took into account different factors, such as the construction period of technologies, the technology cost, of course, emission factors, of course, and all these factors, I would say, they collapse into the type of energy source that you select. And as their nature, we can distinguish between variable and dispatchable. Of course, dispatchable energy sources allow us to match as we desire the demand of data center, while variable energy sources do not have as much flexibility. And this aspect is of particular relevance for the hourly matching methodology. So as IEA, apologies for my Italian acronym throughout the presentation. So as IEA is underlying, hourly matching is pursued by several large technology companies, more and more pursued, but achieving this ambition with variable renewable energy sources especially comes with challenges. And let's focus on which are these challenges. But first of all, why are we talking about the differences between annual matching and hourly matching? So data centers are recognized to be big energy consumer, and thus they are the objective of policies requiring them to be more and more transparent on the performance, the energy performance that they achieve in terms of the use of renewable energy sources and also in terms of energy efficiency. For what concern Europe, there are mandatory policy instruments that require them to disclose information, thus to grant transparency. The most important is the Energy Efficiency Directive, which introduced the obligation for member states data centers with a power greater than 500 kilowatt to disclose sustainability indicators, which have been defined actually in the Commission delegated regulation, and they regard these areas of interest. For what concern the discussion of today, we are mostly interested in energy consumption, use of renewable energy, waste heat utilization too, and power utilization, while other area of target are temperature set points and water usage. These indicators are required by the European directive on an annual basis. And they are mandatory, while on the other side, there are some voluntary initiatives which strive to be more virtuous, let's say. And one example is the energy compacts. Those are voluntary indeed and traceable commitments launched in 2021 by the UN that any organization can adopt, and they relate to SDG number 7, which deal with affordable and clean energy. The one which is most important in this discussion is the 24/7 carbon-free energy, which commits the organization that adopted to ensure that every kilowatt hour of electricity consumption of a given node, this can be a data center or a company or whatever, must be satisfied by carbon-free energy sources at every hour of the day, indeed every day. And we call it, for this reason, 24/7. Its principles are, of course, that there must be an hourly matching. They foster local procurement of renewable energy sources. With this commitment, companies try to supply electricity not only from the grid but out of the grid too, for example through PPAs. There is the intent to diversify the technology that can contribute to the supply of data center and reduce reliance on fossil fuels, especially in those hours for which right now we are relying on them as much. These two sides of the picture, these two methodology, are supported by large large data center company in different ways, and so companies position in one or the other side. But for sure, for example, Google is supporting an hourly matching, and it's applying it in its commitment. Indeed, I've exploited a graph from the Google methodology published in 2018, where they explain how they are calculating the indicator to reach their commitment. And here it comes the first challenge, which in the International Energy Agency report is very well underlined: matching the supply. So the challenge is, once we have, let's assume, a stable baseload demand of the data center, which is the best supply mix so that to decrease the carbon emissions. And in this graph, we see that with the hourly granularity matching, the calculation is difficult. The matching is more difficult because, for example, in this case study, the data center is supplied by PPA too, which provides solar energy, but we know the solar energy is available in the middle of the day, while in the morning and in the evening, we cannot exploit directly electricity from solar power. So the data center must compensate somehow, and in this case, the graph shows through grid energy, either carbon-based or carbon-free. The excess solar power in the middle of the day, of course, is not physically used by the data center, but it's used by someone else. So again, the challenge is to find the best supply mix to align with the baseload demand on an hourly basis. And to do this, renewable energy sources, in this case, we take the example of solar, must be integrated by data technology. We saw in the example that there is the grid to supply the data center, but other renewable energy sources could provide a different production profile, such as wind, to compensate for those hours where solar power is not available. Storage technology can compensate too, because they can store the solar power, the electricity which is not used during the peak production time of the day of solar, and use it instead of in the morning and in the evening, or they can be substituted by dispatchable energy sources too. The International Energy Agency underlined this difficulty, and I reported here a sentence. They say, when solar power alone is procured to cover 100% of annual demand, the share of hourly demand cover can average only 35 to 45%. So this is one of the first challenges. We are now on the supply side, but also on the demand side, there might be challenges. Thomas was telling us how the increased use of artificial intelligence will drive the electricity consumption of data center in the future. And in addition to International Energy Agency studies, there are many analyses trying to assess which is the energy consumption of artificial intelligence. I reported another example from the literature, De Vries 2023, which tell us that which is the difference between a Google search and AI-powered Google search in terms of electricity consumption per request. We see that with a simple Google search, we are around 0.3 watt-hour per request, while with an AI-powered Google search, we reach 7 watt-hour per request. This is one of the aspects on the demand side, but we also wanted to bring into the picture today the fact that demand might be not stable in the future. Data center demand with the use of AI may change because AI is user dependent. When I say user, I may refer to companies, public entities, and research institutes too, and households too. All these users may decide to use AI in a certain time of the day, so that to change the overall data center demand profile, we ask a quick exercise to ChatGPT, so that to obtain a daily hourly demand curve, electricity demand curve for the use of ChatGPT in Italy. Here it shows the difference between weekend and weekdays based on ChatGPT assumptions, and we found out that there is this shape with a peak in the middle of the day, somehow matching the solar profile, but of course this is a quick exercises. More in-depth assessment must be carried out to understand the future data center demand profile. And on this, I will leave the stage to Thomas at the end of the presentation, if he wants to integrate with some insights on what could be in the future the data center demand profile, given the increasing use of artificial intelligence. But I want to go first, before to leave the stage again to Thomas and Filippo, to one last challenge and one last relevant aspect of data center energy demand, energy interaction, let's say, for the future, because data center are most of the time referred to as energy consumers. But sometimes there is also the awareness that they can be producers. So it's indeed the energy efficiency directive itself that is asking data center with a power greater than 1 megawatt to use the waste heat unless they show that it's not technically or economically feasible. And on this line, last year, we supported Enlighten, which is an European data center company, to develop an updated indicator on the basis of the 24/7 CFE score, which could integrate also this concept that the data center could be an energy producer. So what we did is, departing from the traditional indicators, we included the waste heat within the energy perimeter of the data center, but not only. We created an two integrated indicators, including both the consumption of electricity of the data center and the heat production of the data center. On the other side, these indicators are called system indicator because they take a system perspective. Not only they include the traditional unit of analysis, which is the data center, but they also include the consumers in the perimeter of the analysis, because it's the consumer itself that reuses the heat. And again, this is one relevant topic for the future, which sometimes is touched upon, but other times is completely disregarded. So again, if Thomas wants to tell us something more about what could be the role of data center as energy producers in the future, how much they can contribute to the heat production, so that to fuel the entities which use it, such as district heating or swimming pool or whatever. Just to conclude, these are the two indicators that we calculated. They are both integrated and systemic. The carbon-free energy scores that we saw since the beginning of this discussion, and the avoided emission score. In the graph, we see the difference for what concerns the hourly avoided emissions of one of the data centers that you can find in the report, Eschborn in Germany. And we see that when we integrate the waste heat into the calculation, the avoided emission assessment increases. And with this, I close my discussion, leaving the stage again to Filippo and Thomas.
Thank you very much. Thank you very much for your presentation. So, Thomas, you have been addressed by Sarah a couple of times. If you can provide a quick answer to those questions. And then we have several questions coming from the online public that I would like to forward you. But over to you with the questions of Sarah, if you want to answer them.
Sure. Thanks, Filippo. And I think a very, very good and interesting presentation by Sarah. Maybe on the two questions regarding the data center load profile. So first of all, I would say this is an area where I think it would be good for system operators to start releasing data so that researchers can understand this question better, so that energy sector actors can understand this better. It would be good to start having consumption profiles for data centers as publicly available data sets. What we see today is that generally speaking, data centers have a pretty flat profile. AI, as Sarah highlighted, may change this, but it's not exactly clear at this point. So there are kind of two possible uses of AI in this regard. The first is training. And what we see in discussion with power companies is that AI model training typically has a pretty flat demand, but you sometimes see big swings in demand very suddenly as, for example, the training session stops, the results are saved, and then the next session starts. This can lead to a big swing in demand. So this is something that has been a cause of a bit of concern. The second is, the profile for AI-related inference. So this is actually when you query the models. And I think it's not exactly clear to which way this will go. I think the graph that Sarah showed is very interesting. I think there will be a lot of AI-related inference that will be driven by human activity and therefore will follow typical patterns of human behavior, more active in the daytime, less active in the night. I think that's quite understandable. We will probably also see in the future quite some AI-related interactions that are automated. So what is so-called agentic AI, where this is AI agents carrying out tasks online in an automated way. The balance between these is not so clear. I think it's something that we need to watch. My personal perspective is that if we break down electricity consumption between training and inference, inference is going to predominate by far. So as of today, training is probably more dominant, but inference is going to become the dominant workload and therefore the dominant source of electricity consumption. And I think Sarah's hypothesis that inference will be more variable is probably correct, but this is something that we need more data on and so on. Then regarding the question on heat coupling, it's something that we looked at in the report. There's definitely potential for it. We see projects already in the Nordic countries, for example, looking at heat coupling of data centers. There are three considerations that I would bring to the table here. The first is the total amount of heat demand in Europe, for example, if we just look at heat demand from district heat networks, far exceeds the potential heat supply from data centers. And this is just a function of how energy intensive heating is versus data centers. So even at best, data centers could supply a small fraction of network heat demand in Europe. That fraction then shrinks when you start to think about economic constraints. You would probably need to pipe the heat to the demand center. You would need to upgrade the heat to the required temperature because data center waste heat is relatively low temperature, maybe 25, 30 degrees. So you would need to add a heat pump to upgrade it to 50 or 60 degrees. So that adds capital costs and so on. So the sort of number of projects where that could be cost effective is probably relatively small. And then third aspect that I would bring to the discussion is there's quite some challenges around the contractual arrangements and who is ultimately responsible for ensuring, first of all, that the demand is there, and secondly, that the supply is available for heat. And typically data centers operators don't want to get involved in this. They operate data centers, they don't play in energy markets. And so it will require aggregators and different kind of business models to enable us to tap the waste heat from data centers to a larger degree.
Thank you very much, Thomas. So, a couple of questions from the public. One is related to the volatility of electricity prices. Isn't it a concern, volatility of electricity prices related to artificial intelligence? The second one is related to how to safeguard from climate impacts and related financial risk when you deploy artificial intelligence. Over to you.
Yeah, so happy to comment on both, and maybe Sarah wants to come in as well. So electricity prices are a very relevant factor for data centers. There's no question about that. But we also need to put in perspective, data centers are tremendously capital intensive. They're about 10 times more capital intensive on a per megawatt basis than an aluminium smelter. And so most of the levelized cost of a data center is the equipment, not the electricity consumption. So it is a factor. I would say more important than the price per se is the speed of connection. So that is a very relevant factor when data centers are making locational decisions. What we see is that tech companies are actually quite interested in renewables procurement as a hedge against price volatility. So there's quite a lot of interest in the kind of contracts that Sarah was talking about in hourly matching, because it can provide a relevant hedge against wholesale market volatility. On the question of climate impacts, this I think is something where AI is quite an interesting tool. We see a lot of startups and interesting companies emerging that are using AI to monitor infrastructure against natural disasters, but also climate risks. So, for example, companies that are using AI tools for wildfire monitoring. This can be using ultra high definition cameras, remote sensing from satellite imagery, sensing in terms of detecting smoke, and then AI algorithms to process the data and alert if there is a risk that there is a wildfire. This is quite interesting as climate change becomes a more and more a bigger risk to our critical infrastructure, and we see quite a number of interesting solutions being provided with AI related aspects.
Thank you very much. Okay, we can move forward to another question. This is a very short one. You are Australian, but this is related to the old motherland. Is the International Energy Agency collaborating with the UK's AI Energy Council?
Yes, we are actually giving a presentation there next week. So we are indeed.
Okay, so it's a yes. Another question, do you envisage a tech breakthrough in energy consumption for an AI data center in the future? In other words, couldn't be the data center in the future could consume much less?
This is a great question. So first of all, I think it's important for us to understand that there have been tremendous progress in improving the energy efficiency of computing. We're talking about a doubling of the efficiency of computing roughly every 2 years. This is quite extraordinary. We don't see any other energy technology where there has been such a rapid progress in energy efficiency. We made a small calculation that if you had tried to train a model like ChatGPT using the computing technology of 20 years ago, it would have taken roughly the electricity consumption of China today just to train ChatGPT. Instead, it took about 40 gigawatt hours, which sounds a lot, but it's actually not very much. So there have already been huge improvements, and this is continuing. It is quite possible that we will see continued improvements, including breakthrough computing architectures. It's something that we looked at in the report. We didn't quite try to quantify it because it's quite uncertain, but maybe after 2030, we could see breakthrough in new computing architectures that are much more energy efficient. This is definitely something that is being actively researched and prototyped. The other aspect that I would mention here is, it's not just the hardware that is becoming more efficient. The models themselves are becoming more efficient as well. And there is a lot of progress and a lot of scope for progress on that as well. You may recall that in January, a Chinese company released a model called DeepSeek that received a lot of media attention because it was apparently much more efficient to train, but also to operate than existing models. When you look at the details, the picture is actually not so clear for DeepSeek. It does use some very, very interesting architectural innovations that make it more efficient. There's no doubt about that, and that reduce its energy consumption. But at the same time, DeepSeek is a kind of different class of model. So we're starting to distinguish between what we call large language models, like classic ChatGPT, and what are starting to be called large reasoning models. So large reasoning models use much more compute at inference time to provide a better answer to particularly technical questions related to maths or coding, where more compute and calculations can provide a better answer. These large reasoning models are actually much, much, much more energy intensive than classic large language models because they use so much more compute at inference time. They can be as much as 10 times more energy intensive. And the ironic thing is that DeepSeek is actually a large reasoning model. And so it's not exactly clear which way this will go, whether the continued improvement in compute efficiency and hardware efficiency and model efficiency will lead to absolute reductions in energy consumption, or whether there will be a kind of Jevons paradox where if compute becomes more efficient, if models become more efficient, we will effectively use much, much more of it. DeepSeek is an example that actually goes in both directions. And this is why in our report we used a scenario-based approach where we looked at, a potential upside for electricity consumption as well as a potential downside. And part of the downside scenario design is more breakthroughs on efficiency, but also in the way that we use these models.
Thank you very much. I know that you are leaving at 1 p.m. sharp, but maybe there is still room for a couple of questions more. One is related to water consumption. Have you considered it when you consider the cooling purposes?
Yes, we did indeed look at water consumption in the report. So there's a specific box on that. I think the key message from that box is that yes, artificial intelligence and data centers are water intensive, but they're not much more water intensive than other kinds of energy infrastructure. We use a lot of water for power generation, for cooling, et cetera, et cetera. So artificial intelligence, of course, we need to look at minimizing water consumption of data centers, but compared to power generation, compared to agriculture, compared to industry, it's not going to be a dramatic increase in water consumption.
Thank you again. Moving forward, I was wondering if the report includes any section that addresses regional disparities in access to energy. And if so, could you please elaborate on that aspect?
Yes, absolutely. So I think there are two aspects to this. I mean, the first one is, the developed versus developing country divide. So if we look at, where data centers are installed today, there are basically three regions that matter. It's Europe, it's China, and the United States. These three regions have about 85% of installed data center capacity. So it's quite a concentrated industry. And outside of a few special cases, like, for example, Malaysia, there are relatively few data centers in the developing world. And of course, the issue of access to energy is quite relevant here. Data centers are electricity intensive. If there is competition for electricity because, in a developing country, there are a lot of other sources of electricity demand growth. If the electricity network is not so reliable, then there could be a challenge of localizing data centers within developing countries. So energy is a relevant factor there. Even within developed countries, if we look closer to home at Europe, Europe is having quite a number of challenges of localizing more data centers within Europe. And this is also a policy objective when we consider goals like data sovereignty. one of the major barriers to this is the challenge of getting grid connections, because the European system is quite congested already, and building new infrastructure can take a lot of time in Europe. So even within the developing world, the availability of energy at a local level is also quite a relevant factor to where data centers are being developed, and in places like Europe, how quickly they can be developed.
Thank you very much. Then there is a bulk of questions that are related to emissions. So artificial intelligence growth, increasing methane emissions, whether you are considering CO2 capture, and in general, the methodology you use to estimate the reduction in emission brought by AI development. Maybe we can aggregate those if we want to elaborate. Thank you.
Yeah, so first of all, regarding the reductions, so what we did was actually quite an extensive survey of global energy companies across the entire energy sector, from energy supply to consumption. And we basically asked them, what use cases they are currently using for AI in their operations and what benefits they see. In addition to that, we did a literature review, and we basically selected only proven use cases with clear benefits for energy demand reduction. And then we tried to model, if we take these use cases and try and scale them up to the entire sector level, what could the impacts be in terms of energy demand reduction? To do this kind of scaling to the sectoral level, we took into account also constraints. So, for example, if the heating and cooling consumption of the services sector is not digitalized, then you can't make that heating and cooling consumption more optimized and more controllable by integrating AI tools into service sector buildings if they're not digitalized already. So we discounted these kind of factors when we considered the total potential. So I would say our estimate is quite conservative, and we don't assume that it will all be implemented. There are big gaps related to skills and regulation and incentives that would need to be overcome. Regarding emissions, the key thing to keep down the emissions of artificial intelligence is obviously to look at energy efficiency of data centers and AI more broadly, but also to look at clean procurement of electricity. So carbon capture and storage with, say, natural gas generation is a solution that is being explored by a few companies, particularly in the United States. But more we are seeing procurement of renewables, as well as I mentioned, forward commitments to novel technologies like small modular reactors, but also advanced geothermal. There's quite a lot of interest in the tech sector with forward commitments to advanced geothermal technologies that would make geothermal energy more available in more geographical locations.
Thank you very much. We have quite a long question. Maybe it requires a bit of elaboration. We might give a try. Are we at risk of seeing a widening gap between the exponential growth in digital demand and the slower progression of sustainable energy supply? This is maybe a more general topic. I don't know if you have somehow.
I think absolutely. And, that's the point that we were getting to in our modeling of data center projects at risk. There is a real risk that, particularly in places where grids are congested, where it's challenging to build new transmission, where it's challenging to build new generation projects, that data centers could be delayed, and therefore that the energy sector provides a bottleneck on AI development. To solve these kind of problems, we need to make sure that we are making our grids as efficient as possible. So using smart grid technologies to get the most out of our existing grids, that we're looking at reducing permitting times for transmission and generation assets, but also that we start to think about how we can make data centers more grid friendly in terms of how they operate and where they are located. So this is a big agenda for work going forward.
Thank you very much. And I believe our time is over. I thank Thomas. I thank Sarah for your time, for your courtesy today. And I believe that we can close this webinar and see you soon at the next webinar. Thank you very much.
Thank you very
Bye.
much. It was a pleasure. Thank you.
Thank you very much.
Bye.